Hello and welcome to the next video in our series, Introduction to RDF Star. My name is Thomas Cook and I'll be leading you through the presentation today. The previous two videos in the series were getting started with Anzograph, showing you how to use Docker and install Anzograph and also Zeppelin containers. So if you haven't done that, you'll need that for this particular video. We'll be using Zeppelin containers and some sample notebooks. So make sure you've watched that, and then also the Sparkle RDF 101 course previous to this, we'll be building on that as well. RDF Star is an update to the RDF standard that allows for properties to be stored on edges, and this helps to facilitate analytics. It's very important that we're able to store various costs or weights or probabilities on these edges when we do analytics. So I'll walk you through a simple example of what RDF data is and then how we can add RDF star properties to our graph. So here's a simple example. We have a person, Jack, is a friend of a person, Jill, and they both went up this place, the hill. Now, with RDF, we can add properties to these individual entities, to these the people and the hill. So the man, the person Jack is a man, he has a birth date. The person Jill is a woman, she has a birth date, and then the place, the hill, has some properties associated with it as well. So this is standard RDF, but what if I wanted to store properties on the individual relationships, the friend of edge, the went up edges, etc. RDF star facilitates this ability, and so these blue boxes can now be represented in RDF. So on our friend of relationship between person Jack and person Jill, we have met at the hill and the met at date. And for the went up relationship, we can store a date there as well. So these can store both literals as well as other nodes. So this is unique to RDF star, and the edges can actually point to other nodes or entire other graphs. So you may want to do things like store provenance or other metadata, which could be an entire graph in and of itself behind that edge. So how do we do that with the RDF representation? And here is a simple RDF serialization, as we discussed in the previous video. If you load this as a turtle file, you can see here that you have the subject, predicate, and object. We have Jack is a man. That's a fact. That's a single triple. Jack has a birth date. Jack likes Jill. And now we get to these blue triples. Jack is a friend of Jill. And we surround that with an extra pair of angle brackets. So you'll notice that there's an extra pair of angle brackets around this triple, and then we put another property at the end of that. So here we have met at the hill and the met at date. So these are the two properties that you see here associated with that first triple. And that's as simple as it is for RDF star. The syntax for querying this data is the same. If you're querying the properties, you simply exchange these for variables, and I'll show you an example in a moment. But this is the turtle serialization, and the Sparkle will see an example in a moment. So we'll now be taking a look at a demo of public flight delay data analysis, and this is all pulled from a website from the Bureau of Transportation Statistics that tracks all of the US flights. And so we've downloaded all of the flights from June 2003 to April 2019. And that data comes down in a CSV file. There's about 32 columns and about 6 million records. And you can see the different columns shown here. Every record is a flight. So there's a date that the flight happened, the airline, the flight number, tail number, origin airport, destination airport, and then a number of metrics around the delay. Is it a weather delay or arrival delay, etc. So how do we get that into the graph? The first thing that we need to do is define what are the entities and what are the relationships that exist in each one of those records. So we know that every airport has a departure and it's a flight. And then there's also an arrival airport and it has a flight associated with it. And once a flight goes from an airport, one airport to the other, we can connect that with a destination link. So that shows that these two airports are reachable. This edge, this destination edge, shows that those two airports are reachable via a flight that we know about. So as each record comes in, it will define origin airport, a destination airport, a flight, and create an edge called destination. And so this is what the graph model looks like, and this is how it starts to take shape. The rest of the columns from this particular file end up being properties associated with each one of these things. Some of them are properties associated with the airport, some of them are properties associated with the flight, and we also have properties that we'll store on the edge using RDF star. So here you can see a little bit different of a graph representation. So we're not drawing a line or an edge for every single property in our RDF graph. This way we showed in the Sparkle 101 video, we can just assume that those properties are part of the flight node. And here we have the RDF star edge property of distance. So as I mentioned, the airport was one airport connects to another airport. We create a destination edge, and then there's also a distance that's in each one of those records, and we can save that distance as an RDF star property on that edge. So how do we load that data? We use the table syntax and specify the CSV file. And in this case, we're pulling the file from S3 from an S3 bucket, a public bucket. And so we'll make these notebooks available so you can import them into your Zeppelin container and run them, and then it will pull the data from our S3 bucket and load it into your graph. But this table notation defines the CSV location first, and then the rest of these are the different columns in the header associated with that CSV. So at the beginning of this, it specifies it's a CSV. We're loading from global, which means it's a parallel data load. The delimiter is comma, and it is true that this has a header. And so each one of these are the columns associated with it. Year is an integer, month is an integer. You can see the different data types associated with it. Now, this is how we map the different elements from each one of the records into the CSV file. We'll have a separate video on loading data that will get into more detail around this, but here we define the origin airport. That is a type. You can see airport is defined as the type. Here's the destination airport. It is also another type. And here is the flight. It is the type. So for every record that we import, it will have an origin airport, a destination airport, and the flight. And the rest of these are properties associated with these. Again, a later video will explain this in more detail, but you have these as examples you can work from in these sample notebooks. And then here at the top is the edge property. So you can see the double angle brackets surrounding the origin to destination triple. And then there's a distance, and then the associated distance is stored in that predicate distance. One of the nice things about RDF and knowledge graphs especially is the fact that you can combine multiple disparate data sets very easily. So in the top left-hand side, we have flight delay data, but we may also want to connect that with airport info, census data, and FAA aircraft registrations. So we just start linking together the relevant pieces from our graph to build out our knowledge graph, to build out the entire corpus of what we know. And the way that that looks is here is our base graph model that we're starting from. We may add a second database of FAA aircraft registration that comes in connected to each flight. And then from every flight, there's also additional airline information that comes in from another data set as well. And then we may pull in census data and connect that to the airport city associated with that particular airport. Now we can start asking questions from our knowledge graph across all of these different entities. We may want to combine the census data with the FAA aircraft registration as well as the airline information to answer the questions that we have. So once we have our data loaded, we can start asking different types of questions here. So we can find out what are the longest flight segments by distance from Boston, or what are airports less than 400 miles from Boston, or the longest distances between two airports, etc. Down at the bottom, we'll showcase a couple of different graph algorithms, how those are used and how the RDF star properties are passed into the shortest path graph algorithm. Okay. And here's an example of that. So the shortest path is invoked. All of our graph algorithms are invoked through a service call. So you'll see here, we call service, and then we pass in the name of the graph algorithm. And then here are our input parameters. We pick the network, the airline flight network. Our source vertex is Boston. Our destination vertex is Honolulu. We're looking over the destination link or the destination edge, and we're looking at the weight of distance. So our shortest path supports both weighted and unweighted shortest path calculations. Unweighted would just check for the number of hops. So the number of, if you wanted to reduce or minimize the number of connections between your flight from one place to another, you can use an unweighted. If you wanted to calculate the shortest path based on the distance or based on the cost associated, you can store different costs and weights and that type of thing on those edges. Okay, let's take a look at this in detail on how it works. I'll switch gears over to our Zeppelin Notebook, and we'll first load the data. So the data is provided in two Zeppelin notebooks, and you can download these Zeppelin notebooks from the links provided, and there will be numbered 1 and 2. Flight delayed demo 1, load data. The first paragraph or cell in this Zeppelin notebook is our query to load the data. So we took a look at this already before, but here is our origin airport being defined, our destination airport, our flight, and here we have the distance. Let me make this a little bit bigger so it's easier to see. And here we have the RDF star property of distance that we're saving in there. Here you can see where the CSV file is coming from, an S3 bucket, the various header files associated with it, etc. So you can run this. You just click on this run, or you can hit Shift Enter, and that will run that. Okay, the data is loaded now. Now I click here on the second notebook, the flight delay demo 2 run queries notebook. And now I can switch over to the other queries associated here. So here is the Sparkle query to check the top 15 longest flight segments by distance from Boston. And here I'm looking for every airport or any subject with an airport code. We'll call that origin. And then for that subject, any destination with a destination, and then capture the distance into this distance variable. And then I combine the origin with the destination with a small arrow, and I save that as leg, and I filter out all the origins that equal Boston, because I want to know the top 15 longest flight segments from Boston, and so I limit it to 15. The data comes back in tabular format. If you click on this first cell, this first icon here, this is the table format that the query returns. So we can see Boston to SFO, and I also did an order by descending of the distance because we want the longest flight segments. If I wanted the shortest flight segments, I could remove this descending here. But the top 15 are Boston to SFO, 2700, Boston to LAX, etc. Zeppelin also gives you the ability to visualize, and so you can click on these different icons here to draw bar charts, line charts, area charts, etc. Okay. The next one we're going to look at is the airports less than 400 miles from Boston. So here we have our Sparkle query, and you can look at these in a little bit more detail and play around with them. But this one is actually doing a construct, which is required for the network viewer inside of Zeppelin. So this icon, when you use a construct, this icon will appear and will show you a network viewer. And this is just a simple network illustration, graph visualization of the data inside of the query results that you've passed. So these are the airports less than 400 miles from Boston. So I can see Boston and the various airports that are less than 400 miles from Boston. Okay, top 10 longest distances between two airports. Sometimes the editor gets hidden and you can click on this button here that will enable that to show the editor. So sometimes you cannot see the query. You can also put Markdown in your Zeppelin notebook. So this number 3, top 10 longest distances, if I double click on that, you can see the source to produce that. So this %MD specifies Markdown, and then these 3 pound signs here specify a heading, and then that's the text we want for the heading. And so I can just hit Shift Enter, and you can see my Markdown. You can also put HTML and images and other things in the Markdown as well to help communicate what you're trying to communicate about the data analysis that you're doing in the data science notebook. So here are the top 10 longest distances between airports. You can see here Honolulu to JFK is going to be the longest. Top 10 longest flights by elapsed time. Top 10 airlines with the longest average delays. A lot of people are curious to know which airline has the longest delay. All right, well, it looks like in this data set that American Airlines wins the crown for the airline with the longest delays. But you may look for different years or do different analysis by playing with these queries and modifying the queries for different date ranges or airlines of a certain size or that type of thing. So you'll notice that there's some over here you may not recognize the code for. Well, we've imported the airline data set, so now you can link that to pull up the information to get the full name of those as well. Longest 2 segments reachable by Boston. Which segments have the longest average departure delays? It looks like you can see the big jump here for that, the average of that guy. Now let's take a look at PageRank. Our graph algorithms start with PageRank, one of the most popular graph algorithms. This is a centrality algorithm showing the most well-connected entity in a graph based on the PageRank algorithm, which is a weighted algorithm. So it's not only just the number of links pointing or edges pointing to a node, but how many edges do the nodes that are pointing to this one have. So it's kind of a weighted algorithm across those. And so we make it very simple. You simply call the PageRank over the destination link of type airports, and you can order by the rank. And you can see here, if you're familiar with the US airport system, it should come as no surprise that the most well-connected airports based on the PageRank results are the major US hubs of the different airlines. So Chicago, Dallas, Fort Worth, Atlanta, Denver, etc. lead in our PageRank results. So I like this example because it's very obvious to people what the PageRank is doing. Now, the reverse of the PageRank, if you looked at if you ordered by ascending, you would see the least well-connected airports. So you'd see airports that are in Alaska or the Caribbean or other far-off places or small airports that may only have 1 or 2 connections to them. These are different ways that the PageRank algorithm is used to show things that are most well-connected in our graph, the central location, the centrality of the graph, or the least well-connected. That's one of the ways that is done. This is useful for doing things like finding the most influential person or influential researcher through a set of documents, other things like that. Now, the shortest path algorithm, using the weighted RDF star of distance, the RDF star edge of distance. So again, we invoke our graph algorithm through the service call, and then we pass our input parameters. Airline flight network is our graph. The source vertex is Boston, and the destination vertex is Honolulu. And we're looking at the weight of distance. So again, if you don't want the weight, you can simply remove this and it will look at the number of hops, the shortest number of hops to that particular destination. So here you can see the results. So Boston through Salt Lake City to Honolulu, that is the result of the shortest path algorithm. This shows you how you can use the RDF star properties in your graph to invoke graph algorithms using these weights. There's a lot more use cases for RDF star, like I mentioned, metadata, probabilities, putting provenance and other information associated with a particular triple there. But this is just a simple introduction, and please download these Zeppelin notebooks and try it for yourself. And we'll see you on the next video. Thank you.